So today we're going to learn about 4 different kinds of reactions with aldehydes and ketones. We're going to cover chapters 21.10 to 21.13. Our first kind of reaction that we're going to do is called a Wittig reaction. It's pronounced Wittig like with a V because it's German. We're going to do addition of primary amines. We're going to do addition of secondary amines, which gives different products. And we're also going to talk about addition of water, or hydration. So our first reaction is different than anything else you've seen before. It's really interesting. So it uses a carbon nucleophile to convert carbonyls into alkenes. So here's your carbonyl. It can be either an aldehyde or a ketone, so that could be an H or an R. And our Wittig reagent looks like this. 3 phenyl groups, benzene rings, attached to a phosphorus that's positively charged, which is attached to a carbon that is negatively charged and has 2 groups coming off of it. So that Wittig reagent attaches, and what your product looks like is RC. So you still have the same pieces left over from your carbonyl, but instead of being double bonded to an oxygen, now it's double bonded to the carbon that was on the Wittig reagent with whatever pieces it had. It forms one new sigma bond and a new pi bond, and then your byproduct is triphenylphosphine oxide. So let's talk about the Wittig reagent a little bit in detail. So our Wittig reagent, if we draw it out, looks like this. So phosphorus, 3 benzene rings, those are our phenyl groups. And it's attached to your carbon that's negatively charged. We saw what the abbreviation was for it. It's up here. And the name of this is an ylide. So Y-L-I-D-E. And it's called an ylide because it has a positive and a negative charge on adjacent atoms. You can also draw a resonance structure with 10 electrons around the phosphorus because it's a third row element. So you can make that carbon double bonded to the phosphorus. But the way it's drawn here is the way it's going to react. Here's how we make our ylide. First of all, we take triphenylphosphine, lone pair on the phosphorus, and we have some sort of primary alkyl halide. So our phosphorus attacks the alkyl group, the halogen leaves, and then we have our triphenylphosphine stuck on whatever your group is. Then a base is allowed to come in. So if we draw out our reagent, and we draw out our hydrogens, a base is added, and that base will come and deprotonate the carbon, putting that negative charge on your carbon, and now you have your ylide. And whatever your conjugate acid is. So a typical strong base that might be used for this would be something like butyl lithium. Super strong base. So once we've made our ylide, or our Wittig reagent, let's talk about what the Wittig reaction looks like in mechanism. So here's its mechanism. You've got your carbonyl, and you bring in your Wittig reagent. So our Wittig reagent might be a CH2 attached to triphenylphosphine. We just know that there are things coming off that carbon. These electrons attack the carbonyl carbon. These electrons from the pi bond come down and attack the phosphorus. So now our intermediate looks like this. You've got a carbon bonded to an oxygen, bonded to the phosphorus with the pH3, bonded to CH3, or sorry, CH2, which is bonded to that carbon. You still have the R groups on your carbon that were part of your carbonyl. And this intermediate is called an oxaphosphatane. Your oxaphosphatane then collapses. The electrons from the CO go down here. The electrons from the phosphorus to the carbon come up here. And now you have your carbon with your two R groups double bonded to the CH2 or whatever was on the phosphorus, and you have your oxygen double bonded to the PPH3 over here. So those are our products of our Wittig reaction. Sometimes it forms a mixture of E and Z isomers if you're thinking about the double bond, but it works better for some things than other reactions. So let me show you an example. Let's talk about how we decide what the starting materials were for a Wittig reaction. So we want to do retrosynthetic analysis. Here's our example. If we make this in a Wittig reaction, we know that this double bond here is the one that is formed. So 1/2 has to have a carbonyl there. C6H5, CH, double bond O. And the other half has to be bonded to the triphenylphosphine. So PH3P, CH3, negative. Or the opposite can be true. You can have this one bonded to the triphenylphosphine, and you can have the other one. Oops, I was trying to erase. I highlighted. Okay, and you can have the other one be the carbonyl. CH double bond O, CH3. What you want to do if you're trying to decide is to make the Wittig reagent the less hindered one. So if you had an option to make one more crowded and one less crowded, you would go for the Wittig reagent being the less crowded one. So we would go for this option for synthesis. So why in the world would you use a Wittig reaction? The nice thing is you can always know the location of the double bond, and it doesn't give constitutional isomers. You can make alkenes that are not terribly substituted. So for example, if you wanted to make this from this carbonyl, if you did it through a Grignard reaction that was then dehydrated, you could take this reagent, C6H5, this could be attached to your Grignard reagent. If you add those two together, you end up with CH2, C6, CH2, C6H5, OH, and then you could do a dehydration, right? Take off your water using acid, etc. The problem is the product that you end up with could be this one, or it could be this one. And one is not necessarily more substituted than the other. They're both tri-substituted. However, if you use a Wittig reagent and add a Wittig reagent to this guy up here, then you're going to know exactly where your double bond is. It's going to come out of the carbonyl carbon and go straight out. Let's talk about addition of primary amines. So an amine just contains a non-bonded electron pair on a nitrogen atom. And a primary amine only has one R group. So this is the addition of primary amines to aldehydes and ketones. So, example of a primary amine, methylamine. So an amine has a lone pair on that nitrogen, only one thing bonded to it makes it a primary amine. Primary and secondary amines are going to both react, but they're going to give different products. So if we have a primary amine, and we add an aldehyde or a ketone, we're going to end up with something called a imine, or a Schiff base. Make sure you pronounce it correctly. Schiff base. So here's what the imine looks like. There's your imine. So where you were double bonded to the oxygen before, now you're bonded to a nitrogen and whatever R group it came in with. So the mechanism has two steps. It's a nucleophilic addition of the amine and then elimination of water. It's totally reversible, so you have to remove the water as you go along. So let me show it to you. So you have your carbonyl, and as you can imagine, your nitrogen group is going to attack the carbonyl. Electrons go up on the oxygen. This makes sense, right? We've got a nucleophile attacking. You've got your O minus up here, and your NH2 R prime plus. You're going to do a proton transfer, and so the proton is going to transfer from the nitrogen to the oxygen, and you end up with your intermediate that looks like this. OH, NHR double prime. Now that we have our carbanolamine, we can react that. Next slide. Here's our carbanolamine. If you bring in water, or sorry, mild acid that's in water, the electrons from the oxygen can be protonated, the water leaves, and now we have our R group adding, or I'm sorry, our water charged, and your nitrogen can now form a double bond, make the water leave. And water that's in solution will just come in and deprotonate that hydrogen. And so now you have formed your imine. You're ready to go. It's resonant. Your intermediate iminium ion here is resonance stabilized. And so it makes a good imine, I-M-I-N-E, at the end. So you want to be able to protonate the OH to make a good leaving group, but if you have your solution too acidic, it's going to protonate the amine at the beginning and it's not going to be able to attack. So that's why we need mild acid. I'm going to end this video here. There's a part 2 that goes with this video, but I want to make sure I don't run over time.